Welcome to the last session of today. We have two more talks today, and let's welcome Xiangyu again.
You, Kate. Hi, good afternoon, everyone, and good morning, America, Arizona, who's watching in Arizona. In this talk, my name is Xiangyu, and I'm going to talk about improving stableKanren's backward compatibility. Okay, so, outline is pretty simple. So introduction, what's the backward compatibility problem we have in there, preliminaries to do some analysis, how to fix these issues, and we present our fix. It's very simple. Um, and after we fix, we can show some results and have some conclusion in the future work. Okay, let's get started. First, also, quick recap about the Minikanren we all know about. Uh, Same thing for basic operators, equal for unification, flash, pound-d, and run. And this is one of the little bit complex example program. We're going to use it later. It's a revolver. It basically try to see if two input lists are reversed to each other. Um, so for example, in this case, run a very simple query onto empty list. So they definitely are like reversed to each other's. The semantics of the Minikanren is the minimum model semantics. And what's new about the stableKanren? This is an extension of the standard Minikanren. So yeah, two more new operators in stableKanren, nado to do the negation, and then the defineo to wrap the code definition together. One of the example program used in stableKanren is the two persons game. So basically, given you a game board, and your winning move is like after you move, your opponent has no move. So this will be your winning position. So this is a very simple program to describe this simple game board, and the winning condition here is like, okay, where's my cursor? Okay, right here. Yeah, the winning condition is like, okay, if I move from X to Y, so make my opponent cannot make a winning move. So this is my winning positions. And run a simple query to ask, okay, tell me all the possible winning positions. So you will say C, B, and A definitely are the winning positions. And yes, the semantics behind this stableKanren is stable model semantics. So one special thing about this stable model semantics is like, okay, there is a possibility we have an unsatisfiable program. So here is a very simple unsatisfiable program. We have two facts, A and B, but the last the rules is like P is true if A is true and not B is true. So it's saying like, okay, P and not P should be true at the same time, which is unable to prove. So this program is unsatisfiable. If we run a query on this kind of program, even though we can see like A is in fact database as a fact, but it also returned a false. In this case, this is not just false or fail, it's just unsatisfiable. Okay. Unfortunately, this kind of like this extension, the stableKanren, is not a real extension. This stableKanren has some like compatibility with the stable miniKanren programs. So let's see like what kind of issues it has here. So miniKanren, we try to run miniKanren in this stableKanren. We'll have two issues with running miniKanren programs. Okay. The first one is like if we do standard miniKanren programs and we define using stableKanren's defineo. So previously, all the miniKanren program written in like define, we just replace the define with defineo. There may be some issues. We will see in the next few slides. And the second one is okay, these standard miniKanren programs, if they reside with that unsatisfiable in the stableKanren program we just stopped, they are also being affected, like cannot produce a result. So these two things like we try to improve to make sure, okay, under these two scenarios, both standard miniKanren programs is able to produce result like working as expected. Okay, so this is the first issues like the simple standard miniKanren program I have showed before. This is the example query also I showed before, right? So in this case, this program still use define, and then we put it into the stableKanren, it can produce a result, which is good. But once I replace this define, sorry, there's one more thing. And in this case, this relation, like reversal, is not convergible, right? If we try to do like run star, it falls into infinity loops because we can just keep going on and on and on to generate like numerously list to reverse to each other. Like just replace with like a -0, 1, 2, 3, it goes on. So if I change this define to defineo, okay, still exactly the same thing, but we just use the stableKanren's defineo, and we try to run this program in stableKanren. Now it just for one, it falls into the infinity loops. So this is the first issues we try to solve. And same thing, okay, miniKanren program running in stableKanren is using define. It can produce a result, it's good. Now if I add an unsatisfiable program with this miniKanren program together, okay, so this is the unsatisfied program we saw before. Now if I run the query again, boom, there's no result. Okay, so these are two issues really impact this backward compatibility. So we try to fix it here. So some preliminaries about stableKanren. Of course, what's normal logic program and the stable model semantics. But this time we are going through in the very different angles. So as we all know, okay, the only difference between miniKanren and the stableKanren is these not operators and mixed with the loops together. So try to categorize the normal program, but this time do it in different ways. So same thing, we try to use an unfounded set, which is the loops, and the relation between the loops and the negations to categorize. So the first thing, we have the definite program. So it has no negation, right? The second layers in this hierarchy, it will have like tight programs. So for tight programs, only negations, no loops in the program. Now stratified negations. Stratified negation, it has negation, has loops, but these two doesn't like interactive with each others. Lastly, we have the normal programs, and normal program has no restriction. Okay, we are going to use this hierarchy a lot during this talk, so just pay attention to it. Now, what is stable model semantics? Okay, this hierarchy is coming out. So for the definite program, we have minimum model semantics. Okay, it's very obvious. And type program, it also generates a minimum model, even though the semantics, they call it negation as failure. And for the stratified programs, also minimum models. It's well-founded semantics. And eventually, only for the normal programs, it uses the stable model semantics. So it will produce stable models. Okay, so same thing, stable model semantics. Key idea is like, okay, convert predicate to the propositional image, create a radar, compute the minimum model of the radar, and compare the two, okay? Now, what's the properties of this stable model semantics? So one property of this, like, okay, since the loops and the negation, they are mixing up together, so we can further categorize this kind of like negation loops into the even loops and the odd loops. So for the even negative loops, is a very simple example like this, right? So it's just like the Alice and the Bob examples, but in this case, we have like P and Q. Okay, so for even loops, even negative loops, then we have like odd negative loops. So in this case, all negative loops is the unsatisfiable program as we showed before. Now, same hierarchy coming out. For a definite program, we use minimum model, so you always have one models. Tight program, also one models. Stratified program, also one models. But for this normal program, we have like no models, or maybe one models, or maybe multiple models. So the reason is like no models actually is coming from the odd negative loops, and the reason we have multiple models is coming from the even negative loops. So therefore, we have like two types of the negative loops here. And as I mentioned, for negative loops, for even negative loops, it will split the models. So previously you may have only one, and right now once we see these even loops, it will split into two. So in this case, P and the Q, they are two models of this original program. Then for the odd negative loops, it actually will create a contradiction, right? So we can see here it's a contradiction. Like we try to see Q and not Q to be true at the same time. Then if there is no way we can avoid such contradiction, this program is unsatisfiable. So which means there is no models, right? This is all the actual things we need to handle in stableKanren. So for unavoidable contradiction, this definition means like, okay, there's an atom in the normal logic program that can neither be proven true or false because the odd negative loops always creates a contradiction, all right? So our odd negative loop here, actually, this is unsatisfiable. But if we can add one more rule to there, so for example, in this case, if we add one more rule, the last rule here to say, okay, we can prove Q just by using A, now we avoid these second rules. Now this program becoming satisfiable. Okay, so this is why we need some like unavoidable contradiction definition, turning unsatisfied program to the satisfiable program, how to fix it, all the things. That's why like stableKanren, it has to take care of all of these things. But unfortunately, this handling is very coarse. Okay, so same hierarchy here. We already know first three all have only one models. We only care about the last one, right? So stableKanren needs to handle it in the defineo macro. So that's why it's able to reasoning about a contradiction. So basically, stableKanren, what stableKanren does is, okay, we have a positive goal. All the internal macro will complement to generate its negative counterpart. Then in the defineo, it just wrap these two positive and negative goals under the same goal. Okay, with some other extra handling, like all the details we need to handle, all the negative loop or even loops we have to handle, loop handling. Okay, it just because this handling for this hierarchy is very coarse right now. In order to find out this unavoidable contradiction, what stableKanren doing right now is a very coarse. Like, okay, this is a part of the defineo structure. Like in the beginning, you just try to check all the programs defined using defineo. Okay, so in this case, normal program definitely we need to do some extra checking to find out this unavoidable contradiction. But it also does it for the stratified program. Same for the tight program and the definite program. Okay, so this is why. The example program I showed in the introduction session cannot be run under the stableKanren. So now the fix becoming very simple. So our fix is like, okay, we turn this like a coarse contradiction handling into a fine-grained levels. How can we do that? So we introduced a new macro called has negation question mark. Trying to figure out, okay, what type of this program it is. So because the unavoidable contradiction actually introduced by C here are negative loops. So the keyword is like negative. So if there is no negation, then we don't have to check it for it, right? So this is the has negation macro definition. Okay, you just go through all your program definition to find out to see if there is a negation in there. If there's no negation, it's a definite program, right? If a standard miniKanren is a definite program. Okay, so back to this structure. Now we can add one more extra layers, like right here. Like if there is a negation, then we perform all kinds of checkings, right? So in this case, previously we are going to check for definite program, and we turn into no checking. Okay, boom, first problem solved. Simple and easy. Now we're coming to the second problem. Like when the standard miniKanren program resides with the unsatisfiable program together. Like right now, we all use like this run interface right here. We all use this run interface. So run interface at the end of the resolution, It's like right here, okay, all fresh, all the query go. After it finish, it will try to check for the unavoidable contradiction. Okay, so previously we just not adding the definite program into this checking set, and right now it's here like it still performs checking. So how can we just like for example definite program, we definitely don't need to run for the checking, right? So if there's an unsatisfiable program there, it runs checking and it failed. So it's simple. We just turn this run into run partial. So run partial is like, okay, we just recover this run partial from the previous miniKanren, we just remove all this like checking. Now this is run partial. And now second problem solved. So simple solutions, two simple solutions. Now we improve the backward compatibility with the miniKanren in stableKanren's. So as a quick recap, previously we had two issues. First one is a standard program defined using the stableKanren's defineo macro. Right now, we only use the has negation to filter out these things. Okay, if it has negation, we do the checking. If there is no negation, no, we do not check for the definite program, right? And the second thing for the standard miniKanren program reside with an unsatisfiable stable Kanren program. We just use run partial to get rid of these like, extra checkings, and we can also produce a result for it. All right, so far so good. Now we got one extra serendipity, like lucky things. Since we have a run partial now, let's see what happens if we try to use this run partial interface on the stratified negation. Because as we can see from this hierarchy, all these top three levels, they're all like minimum models, right? Only have one model. So if I can do one run partial for definite program, I can definitely do the run partial for these two as well. Okay, so the example is like, okay, let me see, yeah, run partial 1, run partial 2. Yeah, so we use this the final SCC problem as an example to show, okay, how can we use like run partial on the stratified negations. So for the final SCC, it basically saying, okay, given a node, so for example, in this case A, what kind of the nodes it can reach in the final SCC is the leaf SCC in this connected graph. So in this case, A can reach to CDE because CDE is in one of the SCC, strongly connected components. It's in the leaf node. There's no way we can go out anymore, right? So A can reach to CDE for sure, and A can also goes to H and I, this SCC, and A can also goes to K. But for F, it can only has like 3 nodes in the final SCC output. It's the H and I and the K. Okay, so this program, if we write in the stableKanren, so we have a problem instant definitions, and we have this kind of reachable, reducible, fully reduced, and if we look into the relation between these nodos and the loops, it's clearly like the two like didn't interact with each other, right? So in the reachable, we have a loop, but the outside reachable, these nodos, there's no loop for it. So this is the stratified negation. So one lucky thing is like we try to use the run partial interface on the stratified negation. It's like, okay, we receive a huge performance gain because we are for sure this partial result we found is part of the final result, right? So there's no way like there's a contradiction, the existing solution we can throw away to do the computation again. So this is what the checking is doing. So basically try to verify this partial result is the final result, is safe. So this is kind of distinguish between the NP hard problems and the polynomial time things, okay? So if we, on the same problem instance, we use like run partial on the final SCC problem, it takes like 0.01 seconds to get results. But if you use like run interface to do the complete checking to make sure, okay, it's 100% sure, but actually the answer is still the same. It spent like 32.6 seconds. So which means the run partial can also work on this kind of stratified negation, right? Now comes to the conclusion and the future work. Conclusion is very simple. we fixed the 2 backward compatibility issues in stableKanren's. Then for the future work, we probably want to add like a stratified negation detection to stableKanren run interface. So in that case, we will have a smarter run interface. Like the user doesn't have to choose, okay, I know this program is a stratified negation, so let me use run partial interface. Otherwise, I use run. So this is not very smart. It's not artificial intelligence. Okay. So to do that, like for one of the future works, like right here, we already have the highest negation to not checking. So actually, if we have a way to say, after this has to be done during the runtime. Like after the runtime, we know this is a stratified negation, and the partial result is actually the final result, and we don't need to do the checking, right? So same thing like here, we don't need to use the run interface to run on the program. Again, like automatically decide, okay, let's just do run partials. So this is one of the future work. Thank you. I'll take some questions for 5 minutes.
Maybe my general question would be, what kind of programs can we describe using stable minikanren? Can you comment on that? Because like negation is something that everyone wants, but it's intangible, of course, in logic programming languages. So what's the power of your implementation?
So I think right now, one thing is like, okay, if we try to migrate from miniKanren to stableKanren, give the user the confidence, okay, it won't break anything they are using right now, right? Because previously, if I migrate from the miniKanren to stableKanren, I change the define to defineo, and suddenly this program cannot produce results. So this is one advantage. Then the second one, like I mentioned, it distinguished the checking or not checking for stratified negation. So maybe like in the future, the user's problem is actually not that NP-hard stuff. Like, okay, you only use stratified negation, then the performance will be much better. So the user will be more willing to adapt to like this new solver or program. Okay.
Thank you.